Okay, section 10.3, using chords. Okay, if we remember from our previous section, a chord here, okay, a chord again is just a segment with endpoints on a circle. Okay, so if I was just to draw a chord in this circle right here, if we start here, and I was just to draw a chord, okay, so let's call this chord AB. Okay, AB. This chord AB actually divides this circle into two parts. It divides the circle into the parts here that are inside AB. So we would call that a minor. There we have a minor arc, because again that arc has a measure of less than 180, so there we have a minor arc. And then we have the part of the circle outside the chord. Okay, we have this bit I like to call outside the chord. That part we call the major arc. Okay, so a chord actually divides a segment up into a circle. Sorry, a chord divides a circle up into two arcs. Okay, if my chord, again, if you remember from a previous section, my chord could go through my center. If my chord goes through the center, again, we call it a diameter. So there's my chord that goes through the center. So this guy right here we call a diameter. Okay. And so then that diameter then actually divides my circle up into two semicircles. So that right there, again, just some review, is what we call a semicircle. Okay. So this lesson is going to be talking about the chords, the lengths of the chords, and the lengths of those arc measures. Okay. So our first theorem here, congruent corresponding chords theorem. Okay. So first of all, if I'm in the same circle or in just two different congruent circles, two minor arcs are congruent. So we would say this minor arc, this arc here, oh, let's get rid of the highlighter. Let's use a pen instead. Okay. Two minor arcs are congruent. So this arc here is congruent. So arc AB is congruent to arc CD here, if and only if their corresponding chords are congruent. So they are congruent if and only if those two chords are congruent. So this chord here, that segment A to B, and this segment here, C to D. Okay. So these two arcs, so the arcs are congruent if and only if. And again, remember that's an if and only if, so it works backwards also. So meaning, if I know I have congruent chords, if I know these two chords are congruent, then I know the minor arcs that they cut off are also congruent. Okay, so that is our congruent corresponding chords theorem. So if I have congruent corresponding chords, then their corresponding arcs are also congruent. Okay. The perpendicular chord bisector theorem. So if I have two chords that are perpendicular, so if you know here I have two chords that are perpendicular, one of the chords is a diameter. So if a diameter of a circle, so there I have my diameter of a circle, is perpendicular, again 90 degrees, to another chord, then the diameter bisects. If we review what bisect means what? Divide into two equal pieces. Divide into two equal pieces. It bisects not only the chord, but also its arc. So here I have a diameter that's perpendicular to a chord. So if I know we have that 90-degree angle, so since I know that's 90 degrees, since I know this, I know that this distance from F to H is congruent to H to D, and I know this arc from F to G is congruent to G to D. So if e.g., again, it has to be a diameter and perpendicular. If I know it's diameter and perpendicular to a chord, then I know the two pieces of the chord are congruent and the two pieces of the arc are congruent. So that's the perpendicular chord bisector theorem, but then it also has a converse, meaning you can use it the other way around. If one chord of a circle is a perpendicular bisector of another chord. So if I know we are perpendicular, so if I know 90 degrees, and I know the bisector, if you notice here it doesn't say anything about it being a diameter in that first bit of information. So if I know 90 degrees and bisector, then I know the first chord is a diameter. So if I know perpendicular and bisector, then I know diameter. Hypothesis, conclusion. Okay, so let's go ahead and let's use some examples using this. So in the diagram, circle P is congruent to circle Q. So I know the two circles are congruent. Okay, so I have two congruent circles. Segment FG, so that's segment FG right here, that would be this segment right here, is congruent to segment JK, right there. And we know the measure of this arc, oops, sorry, quick scroll. We know the measure of this arc from J to K is 120 degrees. Well, since they're in congruent, so since we know congruent circles, and we have congruent chords, I know the arcs are also congruent. So since we have congruent circles and congruent chords, then I know the arc, I know arc JK, will be congruent to the arc GF, which means their measures are also the same. So that would tell me that the measure of arc GF, or FG, is equal to also 120 degrees. Since we not only have congruent circles, we also have congruent chords. Okay. Here, extra example 2. Ooh, this has got a lot of information in it. So first of all, let's look at the picture and figure out what we know. We want to find KH. So K to H, we want to try to find this piece right there, K to H. Okay. And we want to find the measure, let's go ahead and switch colors. We want to find the measure of arc HLK. So start at H, go through L to K. So this arc right there. Okay. Okay, so first of all, let's look at this picture and see what we know. I'm going to kind of jot down things I know. First of all, I know that JL, J to L, this guy right here, no, J to L right there, yeah, we can switch colors, let's make him pink. J to L, this pink thing right here is a diameter, so I know JL is a diameter. So J to L is a diameter, so if J to L is a diameter, if we notice here, that diameter is now perpendicular to, it's also perpendicular to, so segment JL is a diameter, and it's perpendicular to the chord HK. So we have a diameter perpendicular to a chord. So if we flip back in our notes, if I have a diameter, so here we have a diameter, perpendicular to a chord. Hey, there we go. We can use the perpendicular chord bisector theorem. Then I know the diameter bisects the chord and its arc. So I know it bisects the chord and the arcs. Let's go back to example 2. It bisects the chord. So this chord is bisected. These two pieces are the same. Well, if that's 14, then this one's 14. But it also bisects the arc. So I know this is congruent to that. So I know that if those two pieces are congruent, their measures are the same. So I can set up an equation. I know 2x minus 8 is going to equal 127 minus x. So if we solve that guy, I'm going to add the x to both sides. Okay, and let's add the 8 to both sides. $135. Divide both sides by the 3. 45. So x is 45. So if x is 45, then that tells me that this arc J to H would be 2 times 45 minus 8, which gives me 82. So this one's 82 degrees, which means this one is also 82 degrees. All right, so now let's figure out what are we looking for. Again, we're looking for that KH there in orange. K to H, well, 14 and 14, the measure, oh, we can just go KH because it's talking about the measure. KH then is 14. Now we're trying to find the measure of the green. So if we look at that green, okay, that green, let's see, that's that arc measure all the way around right there. So we're looking for that arc. I know this is 80, so I know here this pink's 82. I know this one's 82, but I know all the way around is 360. So if I take the 360 and subtract the two 82s, that will give me what's left, minus the 2 times 82. I end up getting 196, so the measure of arc HLK is 196 degrees. Which makes sense because if you notice, it's more than a semicircle, because a semicircle straight across would be right about there. So it's more than a semicircle, which is 180, so that makes sense. All right, here's another example. A telephone company plans to install a cell tower that is the same distance from the centers of the 3 towns. So I'm looking for some center inside this, between these 3 towns, P, Q, and R. So it's the same distance. Basically, I'm wanting all of these distances to be the same. So if you notice, if I think of all of those as radii, okay, then we would be the same distance from all 3 towns. Okay. So I'm looking for the same distance from all 3 towns. So really, okay, I'm wanting that point to be the center of my circle. So for it to be the center of my circle, okay, if we think of, let's go ahead now and let's divide, let's go ahead and draw these segments in. If I want this point, let's call it point C right here for center. If I want that point C to be the center of a circle, I want it to be on the diameter. So I'm looking for the center of a circle. And we know diameters always go through the center. So basically, I'm wanting a diameter that goes through that center there. Let's draw that a little nicer. Okay, center C, the radius, radius, radius. So I'm wanting that to be the diameters. So to do that, I'm going to need the perpendicular. I'm going to need the perpendiculars to these 2 chords. Because if it's perpendicular to these 2 chords, then I know it's the diameter. Using this, if one chord of a circle is a perpendicular bisector of another chord, then the first chord is the diameter. So I'm really looking for the perpendicular bisectors here. I want to be perpendicular and also bisectors right there. Okay. So where should the cell tower be placed? Well, it should be placed on the center of the circle, which where would that be? Which is on the perpendicular bisectors, of the 2 segments, of segment PQ and segment QR. So, which is on the perpendicular bisectors of the segment PQ and the segment QR. So if I was to find the perpendicular bisectors of those 2 segments, it would actually get me what the center of that circle should be, right there, my center. And then I could draw that circle. All right, another theorem we have for today. Okay, so here we have the equidistant, same distant chords theorem. So in the same circle, again, that same bit of information, if I'm in the same circle or in congruent circles, 2 chords are congruent. I know 2 chords are congruent if and only if they are the same distance from the center. And again, that's an if and only if, so it goes back and forth. So, and again, we measure distance perpendicularly. So here I know these 2 chords. I know this chord, C to D, and A to B, are congruent if and only if their their distances, their distance, that perpendicular distance, if this distance and this distance are the same. Okay? So they have to be that perpendicular distance from the center. Okay? So here an extra example 4. In the diagram, we know EP equals EQ, which is 12. So E to P, so this distance here from E to P, and E to Q is the same. Oh, that looks bad. Let's redo it. E to P and E to Q, those distances are the same, which are both 12. And it's a perpendicular distance. So I know the two chords are equidistant. The two chords are equidistant to the center. So if I know the two chords are equidistant to the center, centers, there's only one center, then I know that chord AB is congruent to chord CD. So I knew the two chords are congruent. So if the two chords are congruent, their measures are the same. So their measures here are the same. So I know that 7x minus 3 equals 5x plus 7. So if we go ahead and solve that, I'm going to subtract 5x from both sides. So we'd have 2x minus 3 equals 7. I'm now going to add the 3 to both sides. So 2x is going to equal 10. Divide by 2, x is 10. X is 5. So I know x is 5. So if I know x is 5, then I know that this distance here would be 7 times 5 minus 3, which is 27. Nope. 35 minus 3, so it'd be 32. So I know B to A is 32. I also know C to D is 32. Okay. But it's not asking for how long those are. It's asking us to find the radius of circle E. Find the radius of circle E. Okay, so a radius, what would a radius look like? I could draw the radius anywhere. I could draw a radius like that. I could draw a radius right here. Okay, I'm going to choose to draw my radius right here. Oh, no, a little farther over. Right here. Okay, why would I choose that radius? There's my radius R. Right there. What I'm trying to find, because I have now made a right triangle. And I know one of the sides is 12. Okay, and I know then if I was to draw in a diameter through here, it's perpendicular to this chord right here, which means that it bisects this. So if the whole thing, we know this whole thing is 32 because it's the same as this one over here. So if the whole thing is 32, I know this little piece is half of that, which is what, 16? So I now have a right triangle right in here. Does everyone see the right triangle? It's right in here. Let's make it thinner. It's too wide. Right? No, undo. Okay, I have a right triangle right in here. Okay, with legs of 12 and 16, and I'm trying to find the hypotenuse. So I can now come in and use the Pythagorean theorem. A squared plus b squared equals c squared. So 12 squared plus 16 squared equals r squared. Okay. 12 squared plus 16 squared is 400. So then r would be equal to the square root of 400. The square root of 400, I believe, is 20. So my radius is 20. Do we have any units on this? Nope. So radius is just 20. All right. Questions? All right, you now have everything you need to go ahead and get your practice done.